In this video, we are going to see how you can utilize Smith chart to find out the reflection coefficient. So we have some parameters like this reflection coefficient E or I and the angle of reflection coefficient in Smith chart. So we can see if we have the load impedance and characteristic impedance known, how we can utilize this to find out the reflection coefficient. So let's start with our circuit, basic circuit system. So it will be having the source and which is connected to the load through a transmission line. So when a wave is incidenting on it, if this load and the characteristic impedance are not matching, there will be some wave getting reflected back. So this wave getting reflected back depends upon the impedance mismatch between the load and the characteristic impedance, that is given by reflection coefficient. So the reflection coefficient is given by the expression like this. So it is the ratio of the reflected voltage to the incident voltage. So tau is equal to V reflected by V incident. It is related to the load impedance and the characteristic impedance by this expression ZL minus Z0 by ZL plus Z0, where Z0 is the characteristic impedance, ZL is the load impedance. So if you consider this reflection coefficient, this is like a complex number. Its magnitude gives the information about how much voltage is getting reflected back. The phase gives the information about the phase difference between the incident wave and the reflected wave. So it is like a complex number. It will be having a magnitude and the phase. So we have a video on our channel which will be describing more about reflection coefficient. I will put the link in description if you want to know more about the reflection coefficient. So let's see how we can use the Smith chart. So we know that this is the expression for the reflection coefficient. So if we want to use the Smith chart, the first thing we have to do is we have to convert the reflection coefficient using the normalized impedance. So I'm going to divide everything by Z0. So here you can see that everything is divided by Z0. So the expression will be given by ZL minus 1 by ZL plus 1, where ZL is the normalized impedance. So let's see what will be the reflection coefficient if the load is like short, open, or like a purely inductive loads. So let's see that. If our load is actually short, that means that ZL equal to 0. If you calculate the reflection coefficient, we can see that the reflection coefficient will be minus 1. That means it will be 1 angle 180 degree. So in our previous video, we have seen that this is the point for the short. So this actually corresponds to the reflection coefficient of 1 angle 180 degree. If you use the open circuit, that is if our load is open, our reflection coefficient become 1, that means 1 angle 0. So we know that this is the open point. At this open, the reflection coefficient magnitude is 1 and the phase is 0. And let's consider a purely inductive load. Like if the load is inductor, that means ZL equal to 50J. If you calculate the reflection coefficient, it will be 1 angle 90 degree. So in all these cases like short, open and the purely inductor cases like 50J, you can see that the magnitude is 1. So this is the purely inductor case. Here you can see that all the magnitude is same, which is 1, but you can see there is change in the angle. So for the short, the phase is 180 degree. For the open, phase is 0 degree. And if it is a purely inductor like 50J, the phase is 90 degree. So if we draw a circle considering everything, we can see that all the load happening on this circle will be having the reflection magnitude of 1. So this circle represents a constant reflection coefficient circle having the magnitude 1. but the phase will be different, but the magnitude will be the same if we consider any point. Like if you are going to consider minus 50J here, it's the reflection coefficient will be 1. So whatever be the load impedance on this circle, the reflection coefficient will be the same. And if you consider the match, that is ZL equal to 50, which is same as the characteristic impedance, we can see that reflection coefficient is 0. So this is our matched position. Here you can see that the reflection coefficient is 0, and that means that the reflection is minimum here and the reflection is maximum on the outer circle. So if you draw constant circles with the center at this matched point like this, you can see that any load impedance happening on this circle will be having the constant reflection coefficient. So any load resistance happening on this circle will be having the reflection coefficient magnitude of 0.2. So any load happening on this circle will be having the reflection coefficient of 0.4, like that. So if you consider any circle with center as the matched point, the load happening on the circle will be having the same reflection coefficient magnitude. So we can consider this as the constant reflection coefficient circles. And here we can see that as the distance from this matched load point increases, the reflection actually increases. So if it is near to this point, the reflection is less, but if it is actually increasing, the reflection actually increases. So if we have a point, it means if you know the load impedance, how you can find the reflection coefficient using the Smith chart. So here I have a load impedance, which is the normalized impedance given by 0.115 and J 0.174. If I want to find the reflection coefficient magnitude, what I can do, because we know that if we draw a circle with this center here and the point here, it will be on a constant reflection coefficient circle. So if you want to find the magnitude, what you can do is measure the distance from this matched point to that point. So just measure this distance, and on the below point you can see reflection coefficient E or I or reflection coefficient P. So previously we have defined like this, right? So the reflection coefficient is defined as the ratio of the voltage, right? So here you can see that two reflection coefficient. One is given by the expression E or I or the reflection coefficient P. So in our reflection coefficient, we are considering the voltage. So here that corresponds to E. I corresponds to the current. P corresponds to the power. So what you have to consider is the reflection coefficient E or I line. So this is the one you have to consider as we are defining the reflection coefficient in terms of the voltage. So just move this arrow, the distance from here to here to this line. So the same distance, if you move if you move this distance arrow from here to here, whatever point it is touching, which will give you the magnitude of the reflection coefficient. So here you can see that the same distance arrow is hitting on the point 0.8. Here you can see the values like 0 0.1, 0 0.2, 0 0.3, 0 0.4 and 0.8 and up to 1, because 1 is our maximum value. So here the magnitude can be taken as the value 0.8. So now we found out how you can find the magnitude. Next is we have to find the phase. So here you can see that there is one thing marked as angle of reflection coefficient in degrees. So this circle corresponds to the angle. So here you can see that the value is minus 20 here and plus 20 here. So if you In circle, this path you can see the angle ranging from 0, 20, 40, 60, 70, 180 and minus 170, minus 160 like that. So this is the axis which is corresponding to angle of reflection coefficient. So that angle, so if you extend lines to that uh, circle, you will get the reflection angles. So let's see, if you have this point, how to find the reflection angle. So just extend that line to this angle of reflection coefficient degrees axis. So the point which is touching on it will give you the angle. So here you can see that the axis is hitting on 140, 150, 160. So this angles corresponding to it is 160. So you get the magnitude from the exact distance and the angle by extending it. So this is your magnitude and angle. So let's consider a real scenario like this one. If you have a lossless transmission line with a characteristic impedance Z0 equal to 50 ohm, which is terminated with a load impedance 25 plus 25 j ohm, find the reflection coefficient. So we know that if you have to deal with the Smith chart, we have to convert that into the normalized impedance. So find out the normalized impedance. It will be equal to 0.5 plus 0.5 j. So our next step is mark this point on the Smith chart. So here you can see that. So this is the 0.5 constant resistance circle and this is the inductance value. So mark that point here. So we have marked that point, and my next step is to measure the distance from here to here and plot that same distance on this reflection coefficient E or I. So what I'm going to do is I'm going to measure the distance from this point to that point, and I'm going to measure the same distance on this reflection coefficient E or I. So this same distance I am going to measure here. So you can use a scale or compass just to measure this distance, and you can measure the same distance here. So it is given around 0.44. So that is my magnitude. My next step is to find the angle. So to find the angle, what I can do is I can just extend this line, and here you can see that the point which is touching on it. So this is 110 and this is 120. Then it is like 112, 114, 116.5. So that is my angle. 116.5 is the angle. So I got the magnitude from here and the phase from here. So this is how you are calculating the reflection coefficient from the Smith chart. So we can do a cross verification because we know that reflection coefficient is given by this expression. So you can substitute this and you can see that it gives almost the same result as whatever we have obtained from the Smith chart. So using the Smith chart, we can very easily find out the reflection coefficient instead of doing these type of complex calculations. So that is the importance of Smith chart. So nowadays we have lots of calculators, but at that time when this Smith chart was developed, there were no solutions to do these type of complex calculation. It has to be done manually. So the Smith chart was very useful at that time. So I hope you get some idea about the reflection coefficient calculation from Smith chart. Thank you.